Okay, hello everyone. Today we will cover gravitational chapter, and first of all we would be seeing universal law of gravitation. So uh, according to our needs that we would require in J preparation, the main formula we need for universal law of gravitation is that if there are two bodies, so there would be a force of attraction between those two bodies, and that force of attraction is written as G m1 m2 by r square, where m1 m2 are the masses of the two bodies and r is the distance between the two bodies. And here is a vector diagram showing the forces between two bodies m1 m2 m3 and m4. Okay, since the force is attractive in nature, so if we if we see if we see the vector representation of the force, we see a negative sign here, which denotes that the force is attractive in nature. Okay, now consider this system of particles where we see four different masses m1 m2 m3 and m4. So if we try to reduce the force on a single body like m1, so we write that force by this formula: G m1 m2 by r 21 square plus G m3 m1 by r 31 square plus G m4 m1 by r 41 square. And here are these are the unit vectors representing the direction of the force. This is not just simple addition, this is vector addition. Okay. Now we will see acceleration due to gravity on Earth. So suppose there is a particle of mass m on Earth at a distance. Now first of all, let us suppose there is a particle on Earth at Earth's surface. So whenever we are taking the distance between two bodies, we take it from their center of mass. So suppose there is a particle here at a distance at Earth's surface. So the distance between that particle of mass m and the center of mass of Earth is the radius of Earth. So we can write the force as capital G, mass of Earth into mass of that particle upon distance square, that is radius of Earth square. Now, as we know, force is equal to mass into acceleration. So if we want to derive acceleration due to gravity, then we can derive it by acceleration is equal to force upon mass. So this is the term, force upon mass. So here this is the acceleration due to gravity, which is force upon mass. So we get an equation G me upon re square. So this is acceleration due to gravity on an Earth's surface. Now, what happens if the mass is inside the Earth's surface, or it is at a height greater than our radius of Earth? So we may also see it here. Now suppose the body is at a height h. So now we can see the mass is here and the center of mass of Earth is this. So the total distance between center of mass of Earth and the body of mass m is Re plus h. So we can write force is equal to capital G me me, that is mass of Earth, small m, that is mass of the particle, divided by Re plus h, the distance between the two center of mass squared. So the force is written here like this. Now, since we want the acceleration due to gravity at this height, so we may divide this force by the mass small m. So acceleration due to gravity here is written as G mass of Earth divided by radius of Earth plus height whole square. Now there can be cases if the height is very less than the radius of Earth. Suppose the radius of Earth is 6400 kilometers and the height is just 10 meters. So we can neglect the height. We can neglect the height in front of this radius of Earth. Since so we can formulate this as like this. So when we formulate this like this, we find that the acceleration due to gravity at a height h is 1 g times 1 minus 2h upon re. This comes when we apply here binomial expansion. Okay, so since if the height is very less, if the height is very less than the radius of Earth, so the final acceleration due to gravity at a height h is given as g times 1 minus 2h upon re. So this would be reflected in questions also. So now let us move to the next part where if the particle is at a distance d below the earth surface, at that point only the this inner part of the earth would be applying force on this particle of mass m. That outer part would not be able to apply force on this particle of mass m. So we will consider the mass of this part of earth only. Now suppose we can we can we can know the mass of this part of earth by unitary method. Therefore, after applying unitary method, we say m dash is this mass of this part of the earth. So we get that mass. Substitute the mass of that part here as ms, and the distance between the particle of mass m and the center of mass of that part of earth is re minus d. So we write it this like this. Now we know that ms is equal to me times re minus d upon re whole square. So we substitute it here. We get this equation after substituting the mass of the leftover part of the Earth's body. If we divide this by the mass of the particle, we get the acceleration due to gravity when we see any mass at a distance d below the Earth's surface. So here is the final expression. So we can learn that if a body is at a height h above the Earth's surface, so the acceleration due to gravity is multiplied by a factor of 1 minus 2h upon re. And if the same body is at a distance d below the Earth's surface, the acceleration due to gravity becomes 1 minus d by re times the acceleration due to gravity on the Earth's surface. Now we will be seeing gravitational potential energy. the formula that we would be using for gravitational potential energy is this. The gravitational potential energy is defined as work done per unit mass to displace it from point 1 to point 2 under the action of gravitational force. These are the formulas that would be helpful in doing questions of gravitational potential energy. Here, suppose there is a particle of mass m and it is experiencing Earth's force of gravitation. So the force is G-ME-M upon R square. So to write down the work, write down the work being done upon the particle of mass m, we would use integration here. Suppose we are taking it from a distance of r2 to a distance of r1. So we integrate this from r1 to r2. After integration, we get this formula minus g me m 1 by r2 minus 1 by r1. After calculating this formula, after calculating this, we finally get the potential as minus g m1 m2 by small r. So basically, in the questions, we would be using the gravitational potential as this formula only, minus g m1 m2 by r. So let us see an example. Find the potential energy of a system of four particles placed at the four vertices of a square of side L. So for this, the gravitational potential would be, since there are four particles, so we would see interaction between every particles. So this particle would be interacting with this and this particle. So this is length L, this is length L, and this would be root 2L. So here this interaction is written in these terms. Also, since there are four particles, 1, 2, 3, 4, and we have to select two particles to write their interacting potential. So there would be 4C2 terms that would be coming here. So there are a total of 6 terms that came here, telling the interaction between the four particles. On solving this, we get this minus 5.41 g m square by L. Okay, now we would be seeing escape speed. So how do we define escape speed? Escape speed is the speed with which a particle at Earth's surface is ejected, through which, if it goes to a point where there is no interaction between that body and the Earth. So suppose the energy of the particle at Earth's surface is half mv square plus gravitational potential W1. So since energy, so here we would be using energy conservation to find the velocity that should be imparted to the particle so that it escapes the Earth's gravitational field. After doing these calculations, we finally get to a point where we write the minimum velocity that is required at the Earth's surface to eject the particle so that it escapes the Earth's gravitational field is written as root 2 g me by re, which can be finally deduced in terms of acceleration due to gravity in terms of root 2 g re. Now we may see orbital velocity of satellites. So we know that if a satellite is performing rotational motion, if a satellite is revolving rotational, if a satellite is revolving around Earth, so it needs a centripetal force. That centripetal force is given by Earth's gravitational field. So that can be written as mv square. Now, first of all, let us suppose the satellite is at the edge from the Earth's surface. So the centripetal force would be written as mv square by re plus h. Now we know the force of gravitation between them would be capital G small m me upon re plus h whole square. Now if we equate these two, we get v square is equal to capital G mass of Earth upon radius of Earth plus h. So the orbital velocity of a satellite revolving around the Earth can be written as v is equal to root of capital G me upon re plus h. Now we may see energy of an orbiting satellite. Suppose the satellite which is revolving around the Earth will have a gravitational energy, will have a gravitational potential energy plus a kinetic energy. So first of all, let us see the kinetic energy of that orbiting satellite. So we can write the kinetic energy like half with as half mv square. So we know the velocity of an orbiting satellite is root of g me upon re plus h. So we can write the kinetic energy like this. Further, we can also write the potential energy of that satellite in the form of minus g small m mass of Earth upon re plus h. This came from the formula that we reduced, that is minus g m1 m2 upon distance between the center of mass of the satellite and the Earth. Therefore, the total energy that the satellite would be having is kinetic energy plus potential energy. Their summation would be this thing. Okay. Now we may also see geostationary satellites and polar satellites. For geostationary satellites, their time period is equal to 24 hours. So we can write this equation from Kepler's law, that is time period whole square is equal to radius cube. Time periods whole square is proportional to radius cube. So this was some of the theory of this chapter, gravitation. And first of all, there are only some of the formulas you need to know to proceed with the questions. So the basic formula that you need to know is variation of acceleration due to gravity with with a height h and a depth d. So this is given as so this is the formula for variation of acceleration due to gravity with height h, and this is the formula for variation of acceleration due to gravity with a depth d. After this, what you need to remember is gravitational potential energy. Gravitational potential energy is minus g m1 m2 by r. So finally, you have to remember this thing. Then you will need to remember escape speed. Escape speed can be written as root 2 capital G mass of Earth upon radius of Earth. And if you want to write it in terms of acceleration due to gravity, then it can be written as root 2 small g re. After this, we will remember what is uh, what is the velocity of an orbiting satellite. So this would be the velocity of a satellite that is orbiting and that is orbiting around Earth. The total energy of an orbiting satellite can be written as minus g small m capital me upon 2 times of radius of Earth plus h. These are some of the formulas that you will have to learn, and these will help you out with the questions. Now let us move to the questions. Okay, so this is a question which came in JEE Mains 2023 15th April morning shift. So the question goes like this: two identical particles, each of mass m, go around a circle of radius a under the action of their mutual gravitation attraction. The angular speed of each particle would be. So here it is asking us to find omega. So how we can solve this question is, first of all, we know if there are two particles, so there would be a force of attraction between them. And that force of attraction can be written as force is equal to capital G m m upon r, the distance between them square, d square. So if they are revolving in a circle of radius a, so the distance between them would be 2a whole square. Okay, so the centripetal force can be written as m omega square a, or also we can write it as mv square by a. So since we need to find the angular velocity, so we write it as m omega square a. This would be equal to g m square upon radius whole square. Since the radius is since this r is the distance between the two particles, so the two particles are at diametrical opposite points. So we write r as 2a. So here m omega square a is written as g m square upon 2a whole square. Simplifying it, we would get omega as, so simplifying it, we will get omega as this option, root of gm 4a cube. So this would be the answer. Now let us see the next question. Body is released from a height h equal to the radius r of the earth. So here the height is equal to re. The velocity of the body when it strikes the surface of earth would be. So this question can be done with conservation of energy. Now suppose when the body is at the height is equal to radius of earth, so at that point the body has zero velocity since it is released from that height. So the only energy at that point the body have is gravitational potential energy. So at that point the energy can be written as minus g small m capital M upon r upon 2r, that is capital R plus h. Since h is equal to r, so we can write it as minus g capital M small m upon 2r. And let's suppose when the body strikes the earth's surface, its energy would be gravitational potential energy and some kinetic energy. So that would be minus g capital M small m upon r plus half mv square. From this point, from this from this from this equation, we can derive the velocity of the body when it strikes the surface of Earth as v is equal to root capital G m upon r. We can replace this capital G m upon r. We can multiply here in the root by r here and r in the numerator, and we can replace this G m upon r square with small g. So this can be written also as root gr in terms of acceleration due to gravity. So this becomes our answer, that is root small gr. Now let us see this question. Two planets A and B of radius r and 1.5 r have densities rho and rho by 2 respectively. The ratio of acceleration due to gravity at the surface of B to A is. Now, first of all, to find acceleration due to gravity, we need the mass of the bodies A and B. So to find the mass of the bodies, we would use densities. So acceleration due to gravity due to body A would be capital G mass of A on radius of A whole square. Replacing the mass of the body A by 4 by 3 pi Ra cube. So we get this into density of A. Similarly, we write the same equation for gravity of for the body B. So acceleration due to gravity would be this thing. Now to find the ratio of acceleration due to gravity at the surface of planet A and B, we can divide the expression Ga and Gb. After doing this, we get the ratio of the acceleration due to gravity of the body B to the body A as this. So finally, our answer becomes 3:2. Okay, now let us see this question. So the statement one says, for a planet, if the ratio of mass of the planet to the to its radius increases, the escape velocity from the planet also increases. So we know escape velocity is equal to uh, root gme upon radius of Earth, root 2 gme upon radius of Earth. So if the ratio of mass of the planet to its radius increases, escape velocity from the planet also increases. The statement 2 says escape velocity is independent of the radius of the planet. So we can clearly see that statement 2 is false. So our answer would be B or C. Now to check if statement 1 is true or not, we can see the formula of escape velocity. Now we know the formula for escape velocity is root 2 g mass of Earth upon radius of Earth. So this is saying if the ratio of mass of the planet to radius increases, the velocity of the planet also increases. So yes, we see the ratio mass of Earth to radius of Earth in the equation. So the escape velocity is directly proportional to the root of the ratio of the mass of the planet to its radius. So since that value increases, escape velocity will also increase. So our answer would be statement 1 is correct, but statement 2 is incorrect. So B would be our answer.